So I'm going to focus on pulling this example from your homework. Here's a system of differential equations, and then it's the usual deal. We want the general solution, then maybe we want a solution that satisfies a certain initial condition, and we want to describe what's going on qualitatively in the phase diagram. So let me copy this over. There it is, and let's immediately write it in matrix vector form. So when I write x vector, that means I'm talking about a package containing two functions like this, x of t and y of t. So now I can say x prime of t equals matrix times x of t. That's my differential equation. And the matrix is -5, -10, 2, 3. And I want the eigenvalues and eigenvectors for this matrix so I can start constructing solutions. Alright, so let's get the characteristic polynomial. Determinant, let's call this matrix A. Determinant A minus lambda identity equals, and I'm being lazy here. So A is, I want determinant A minus lambda. Can I do identity? Identity matrix? How does that work? Identity matrix brackets n. I want the 2 by 2 identity matrix. Okay. There it is, simplified down for me, so I don't have to do any algebra. Characteristic polynomial is lambda squared plus 2 lambda minus 35. All right, eyeball that for a second. No idea how to factor that. Quadratic formula. So the roots of the characteristic polynomial are -2 plus or minus the square root all over 2. And what's under the square root? 4. That's minus 4 times 35. Actually, it's a minus 35 here. And what's under the square root does not look negative. So I must have done something wrong. And in fact, now that I look at this, I can factor it pretty easily. And I'm going to get real. Okay, that wasn't supposed to happen. Sometimes being lazy doesn't pay off. I had just made a typo here in typing in the matrix. Okay, that's better. So lambda squared plus 2 lambda plus 5 is what I should have gotten. All right, now I stare at this and actually think about it, and I think I can't factor this very easily. And now I really hope if I set the problem up correctly that I'm going to get complex eigenvalues. That's the whole point. So -2 plus or minus square root of something that I hope is negative all over 2. And under the square root we have 4 minus 5 times 1. 4 times 5 times 1. Okay, just quadratic formula basically. And now I'm happy. What's under the square root is negative. Well, I'm only happy because that means I didn't mess up coding your homework problem here. It's supposed to have complex eigenvalues. That's the reason I'm happy. Okay, so let's do this division by 2. Let's say -1 plus or minus sometimes I find it easier to just stick this 2 in here inside the square root instead of dividing by 2 outside, divide by 4 inside. Then I have smaller numbers to think about. I have -1 plus or minus the square root of 1 minus 5. So square root of -2, also known as I square root 2. Nope, what is wrong with me? It was 4, 1 minus 5 is -4, so square root of -4 is I times the square root of 4, which is 2, I times 2. So I get -1 plus or minus 2i. Okay, usually you get grosser numbers than this, but I just set up the homework problem to give you nice numbers typically. So I'm not always assuming you have Mathematica or something like that on hand. I try to make the calculations not too horrible. Okay, so immediately we can draw conclusions about the general solution. Once you see the eigenvalues, immediately you can draw some conclusions. -1 is the real part of our eigenvalue, right? It's negative. So our general solution is going to have e to -1t as a factor out in front. So all solutions decay towards the origin. So immediately we know that this is going to be some kind of stable situation. All solutions decaying towards the origin. The origin is in equilibrium. Now we know it's a stable equilibrium. If you perturb away from the origin, you're going to go back to the origin, no matter which solution you're starting with. All right, so that's a lot of information to get just out of the eigenvalue, but there's still more work to do if we want to write down the general solution. So let's say I want an eigenvector to go with lambda, so let me call that v, as I've been doing. And let's say the components are v sub x and v sub y. And let me make this part separate here. I only care about one of the eigenvalues of lambda, so let me just pick one. I'm going to pick -1 plus 2i. So let me just focus on that one, and then I'll find the eigenvector for that one. And then I will automatically know that if I just complex conjugate both lambda and v, then I'll get the other pair, if I needed it. But I don't even need it. Okay, and I forgot what the matrix was. -5, -10, 2, 3. Maybe I'll write that here. Okay, and my goal is to find what is an eigenvector that goes with lambda. So subtract eigenvalue from the diagonal of the matrix. So +1 minus 2i. All right, and I get that, and then let me simplify. There we go. And by the way, what I'm writing here is a minus lambda identity. And yeah, as usual, I only need one of the two equations that I'm going to get, right? So I'm trying to solve a minus lambda identity, this matrix, times v equals 0. I'm trying to find the null space of this thing. I only need one of these equations, because this is a matrix with determinant 0. So I see smaller numbers. I don't like this 10. I see smaller numbers in the second equation. I'm going to go for that one. The second equation will be 2vx plus 4 minus 2i vy equals 0. So that's the second equation. And then just find anything that satisfies that. Here's a trick that actually always works when you just have sort of a linear combination of two unknowns like this equals 0. You can make this one, if you just want to quickly get a solution, just make this one be the coefficient in front of that one, and then make that one be the negative of the coefficient in front of this one. Like that. So, of course, I'm not saying that that's the solution to this equation. It's just one of the infinitely many solutions, and I just need one, and this is an easy one to write down using this trick. You see how if I just substitute this in there, and that in there, the terms are going to cancel and I'll get 0. So that's just a quick way to get one solution. All right, there's my eigenvector. And now I immediately know what the other one is going to be for the other eigenvalue. So for the eigenvalue that has a minus sign here instead of a plus sign, the corresponding eigenvector will just have a plus sign here instead of a minus sign. That's what we were saying back here, where we were saying they come in these complex conjugate pairs, with the eigenvector also just getting complex conjugated. Okay. But anyway, I don't care. I don't need I'm going to get rid of this red stuff because I don't need a second pair. So let me show you explicitly now what is meant when I write, earlier I was writing v equals w plus iz. What was meant there is, here it would be 4, negative 2 plus I times negative 2, 0, right? So there's like the thing I was calling W, and this one I was calling Z. So now actually if I want to, I can just go and follow this as a formula, just use this as a recipe for creating the general solution. Since I have my alpha and beta and I have my W and Z, right? W is this and Z is this. But I guess I'd rather not. I always like to start from, even when I'm just doing calculations by hand, I like to start from some sort of fundamental nugget of information that I don't need to memorize. So I wouldn't want to just memorize this stuff. Here's something that I would never forget, and that you should never forget after this course. E to the eigenvalue t times eigenvector is a solution. This is how we build solutions. So anytime you've got x prime equals a x, eigenvalue eigenvector pairs lead to solutions like this. This is super easy to remember. So that's going to be our complex solution. Let me just call it x of t. So that means, what was our eigenvalue? Negative 2 plus 2i? So negative 1 plus 2i. So we have e to the negative 1 plus 2i t times v is this. And that is our complex solution. Now, how do I get real solutions? Expand things out. So this is e to the negative t times e to the 2it. E to the 2it is cosine 2t plus I sine 2t. And then this vector here. And then just multiply this out, which I have done here. So I've collected together the real stuff, the stuff that doesn't have a factor of I and the stuff that does have a factor of I. And then now I can say, I can pick off the real and imaginary parts. Let's call those x1 of t and x2 of t. So x1 of t will be e to the minus t times this stuff. Just like that. And x2 of t is e to the minus t times this stuff. And don't try to include the I there. We're going for the imaginary part, which is this real thing that's getting multiplied by I. E to the minus. There it is. And now our general solution is a massive thing. It's a linear combination of these. But you can collect terms and write it in kind of a nicer way, I guess. So initially, we've got kind of C1 times, let's make that green, C1 times the green stuff plus C2 times the blue stuff. And there's our general solution with the free parameters C1 and C2. You could also, in the green terms, you have scalar function times 4, negative 2, and scalar function times negative 2, 0, and then the blue terms also has something times negative 2, 0 and 4, negative 2. So you could collect together all the scalars that are sitting in front of one vector and all the scalars sitting in front of another vector if you want to. That's just another way of writing things. So maybe something like this. So let me write 4, negative 2 here, and then put just some big scalar in front that will have sort of this stuff here times the C1, and also, okay, I didn't make enough space for that. So we'll also have, so negative 4, 2, I also have the sine 2t in this thing and the C2 sitting there. Just like that. And then I've also got, plus stuff times some scalar times the vector negative 2, 0. So what is the green contributing? It's contributing negative c1 e to the minus t negative, the negative coming from here, sine 2t. So and the blue seems to contribute in front of negative 2, 0, e to the negative t cosine 2t. So it's kind of up to you if you want to group things like this, where it's all the stuff that has a c1 in front of it plus all the stuff that has a c2 in front of it, or you can group things like this, where it's all the stuff that is scaling this vector plus all the stuff that's scaling this vector. One thing I would not recommend, however, is splitting this up into x and y, like writing out the components. At least don't do that until you reach the very last step. So whatever it is you're looking for, keep everything packaged together until you reach that last step where you finally need to know x and y. So like in these problems, it's when you reach here. Up until you're like just about ready to input your answer into WebWork, everything should be packaged together in vector form. And yeah, you can imagine how confusing it would get to try to keep track of how x1 and x2 are linked together exactly if they're not written in vector form. And also keeping things in this form makes it very clear that you have two unknowns here, c1 and c2. So two initial conditions, or if you like, one two-dimensional initial condition, one vector-valued initial condition, is enough to know those two unknowns. All right, so great, we have our general solution, and in the next video, let's try to make a phase diagram and actually look at what this looks like.